Welcome to the lecture on transform calculus. So today we will discuss various type of integral transforms, mainly Fourier transform and Laplace transform. So first I will start with the general idea of integral transform. So an integral of the form a to b kst ft dt is called an integral transform of ft. So basically what we are doing here, the function ft we are transforming to another space S. So this is basically a transformation from a t space to the space S with this integral. So here the function kst is called the kernel of the transform, and the parameter S, which is independent of t, belongs to some domain on the real line or in the complex plane. We will come to the detail of the kernels and the range of S while going for the particular transforms. So choosing different kernels and different values of a and b, we get different integral transforms. So for example, we have Laplace, Fourier, Hankel and Mellin transforms depending on the kernels and the range of the integral. So in this lecture we will mainly concentrate on the Laplace and Fourier transform. All these integral transforms enjoy common property, and that is the linearity because of this integral. So let us have a look on this. So if we have an integral transform and we apply to a linear combination of two functions, so we can take here n functions. So let us take for simplicity these two functions f and t, and if we apply the integral transform on the linear combination of these two functions, that is alpha ft plus beta gt, alpha and beta are some constants. So by the definition of this integral transform, we have limits from a to b kst and the function, that is alpha ft plus beta gt dt, and then we split this integral into two integrals. That means the alpha is a constant we can take out. So alpha integral a to b kst ft, and that will be again integral transform of ft, and then the second integral we take this beta out, and then we have integral a to b gt dt. So that is the integral transform of gt. So all these transforms, because of this integral, they enjoy this linearity property. So we will apply this today itself while discussing the particular case of Laplace transform. So now, as we have discussed that this Laplace and Fourier transforms will be discussed in detail in this lecture. So for example, if we take this kernel k, st is equal to e power minus st, the lower limit of the integral 0 and the upper limit infinity, then this improper integral, that is the integral transform 0 to infinity e power minus st ft dt, is called Laplace transform of ft. The second case, for the Fourier transform, if we set this kernel kst is equal to e power minus st ist and a the lower limit minus infinity and the upper limit plus infinity, then this integral transform minus infinity to plus infinity e power minus ist ft dt is called Fourier transform. So this I as clearly the imaginary unit, that means this I square we have -1. So, this integral transform is called Fourier transform of f t. These transform has various applications. For example, and the one of the most important application, that is for solving the integral and integral differential equations, or also integral partial differential equations, the ordinary and partial differential equations. They are also used for in some cases for evaluating some complicated integrals. Okay, so this basic idea of the transform for solving the integral or in general the differential equations, I will explain once again. So, here we have, for example, the differential or integral equations, and if we directly try to solve these equations, it may be difficult to get the solution of these differential or integral equations. So, how these transform helps to get the solution, this is as follows. So, here if we take the integral transform of these equations, then we get this algebraic problems or ODEs. So, simply these complicated integral equations or partial differential equations we can convert by the integral transform to algebraic problems or ordinary differential equations, and they are easy to solve. So, we can easily get the solution of this transformed system or the solution of this algebraic or ordinary differential equations. So, here we get the solution of the transformed system, then we need to go back to the solution of the original problem, then we have to take the inverse transform, and in this we get the solution of the original problem. Okay, so that was the basic idea of the integral transform, and now we will go to the particular case of Laplace transform. Okay, so in this case we have already discussed this case. So, the Laplace transform of a function, just to recall this, is defined as the Laplace transform of f t. So, we will use notation L for the Laplace transform or the Laplace operator on f t, and we will denote this by this big F as a function of s, and this is 0 to infinity, the kernel is e power minus s t f t dt. Provided, and that is very important, this will be called Laplace transform, of course, if the proper integral converges for some s. What do we mean by convergence of the integral? So, just to recall, the integral 0 to infinity e power minus s t f t dt or any improper integral is said to be convergent or absolutely convergent if this limit r tending to infinity 0 to r e power minus s t f t dt exists as a finite number, or this integral is said to be absolutely convergent if this limit r tending to infinity 0 to r with the absolute value of this integral the dt exists as a finite number. So, basically in this Laplace transform we will be discussing the convergence of this integral. Okay, so now we go to the Laplace transform of some elementary functions. So, we take the first example, and that is a simple function. It is a function of t is equal to 1, it is a constant function 1 for t greater than or equal to 0. So, in this case, this Laplace transform of f t, as per the definition, we have 0 to infinity e power minus s t and the function of t, that is 1 in our case, dt. We can integrate this easily. So, we have e power minus s t over minus s and the limits 0 to infinity. So, first the upper limit and then minus we set the lower limit. So, we assume first that s is real and positive. Then what will happen when t approaches to infinity? This term will vanish, and as t tending to 0, we will get here 1 over s. So, simply the Laplace transform of function 1 is 1 over s, because the upper limit here is 0. What will happen if we take s to be a complex number? That means the s we take is equal to x plus I y, and in this case as well, when we take s to be a complex number, the Laplace transform of f t will be 1 over s, and the reason is that again in this case, when we have s a complex number, the upper limit when we take when this t approaches to infinity will be again 0, and we can see that. So, if we take this limit r to infinity e power minus, and for this s we write now x plus I y in the complex form and this r. So, what we have, the r tending to infinity e power minus x r, the absolute value, and the absolute value of e power minus I y r, and this is 1, simply because e power minus I y r is nothing else cos y r minus I sin y r, and if you take the modulus here, e power minus I y r, and that will be sin cos square y r plus sin square y r, and that will give us 1. So, this term is 1, and as r tending to infinity, this will again go to 0 if this x is positive. So, we have the condition that this limit, the upper limit is 0, the term is 0 for real s positive. So, finally, for the general case, we have the result that the Laplace transform of 1 is 1 over s for real s greater than 0. So, let us take another example, and that is also very important. So, this is the Laplace transform of e power a t, or very similarly we can get the Laplace transform of e power I a t and e power minus I a t. So, we first take this Laplace transform of e a t, and that is the Laplace transform of e power a t as per the definition 0 to infinity e power minus s t e power a t dt, and then we can combine these two to get e power minus s minus a t dt 0 to infinity, this integral. And again it is very similar to what we have done for finding Laplace transform of 1. So, we have here e power minus s minus a. So, again if we can integrate this, and this is nothing else e power minus s minus a over s minus a, and then the limit 0 to infinity. So, again if this s minus a is positive, let us take s to be real. So, if this is positive, then again when t approaches to infinity, this limit will be 0, and as t approaches to 0, so we will get simply 1 over s minus a. Again we can also think about the general case here, that real s is greater than a. and the steps are very similar what we have done for the Laplace transform of 1. So, we can assume this again as to be x plus I y and break into the complex and the real part, and again we will see that while putting the upper limit here t tends to infinity, this term will vanish, and then we have again 1 over s minus a in this case as well. So, let us take one of the two functions here, e power I a t or e power minus I a t. So, we consider this e I a t, the Laplace transform, and again as per the definition we have 0 to infinity e power minus s minus a t. So, e power minus s the kernel, and then e power I a t we have the function, and then this dt. So, again we integrate this to get e power minus s minus I a over minus s minus I a t and limits 0 to infinity. And again if we assume that this real s is positive, this term will vanish as t approaches to 0, and we will remain again with 1 over s minus a as t approaches to 0. But we can see this once again. So, the limit r to infinity e power minus s minus I a r and minus s minus a, how this approaches to 0. So, this is anyway independent of r. So, we have minus 1 over s minus a, and then the limit r to infinity e power x, we again assume x plus I y. So, we have e power minus x r, and then minus I y we put here. So, we have e power minus I y, and then we have again this a I we have taken common, and then r, and this part the modulus of this again will be 1, and then we have e power minus x r, and we assume that x is positive, then this will go to 0. So, similarly we can get the Laplace transform of this e power minus I a t, and that will be 1 over s plus I a. So, let us move to the next example, and this is the Laplace transform of t power n. N the positive integer. So, 1, 2, 3 and so on, natural number. So, very useful function, and we will apply later on in the lecture the Laplace transform of t power n. So, as per the definition we move. So, we have t over t power n. So, e power minus s t t power n dt and 0 to infinity. So, we integrate this by parts. So, t power n as it is, the integral of e power minus s t. So, e power minus s t over minus s, and the limits 0 and infinity minus 0 to infinity, again the integral of e power minus s t, that is e power minus s t over minus s, and the differentiation of this function, that is n t n minus 1 dt. This will go to 0 as t approaches to infinity because of e power minus s t, and also it will go to 0 as this t approaches to 0 because of this t power n. So, this term will vanish, and then we have here n over s and 0 to infinity e minus s t t n minus 1. So, what we see again, this is nothing else but the Laplace transform of t power n minus 1. So, we got n over s and Laplace of t power n minus 1. So, we got a recurrence relation here that Laplace of t power n is n over s Laplace of t power n minus 1. So, if we put n is equal to 1, so we have Laplace of t. So, that is 1 over s and Laplace of 1, because n is 1. So, it is t power 0, it is 1. So, Laplace of 1 we know already, that is 1 over s. So, we have 1 over s and 1 over s. So, 1 over s square. Also, if we put n is equal to 2, we will get the Laplace of t square, and this is 2 over s, and the Laplace of t is 1 over s square. So, we will get 2 over s cube. In fact, for n is equal to 3, we will get 3 over s from here and the 2 over s cube from Laplace of t square. So, we will get something 3 into 2 over s cube. So, in general we can also write this is factorial 1 over s square, and this is nothing else but the factorial 2 over s cube. Based on this, now we can prove by mathematical induction that the Laplace transform of t power n is factorial n over s n plus 1. So, if we assume that Laplace transform of t power n is factorial n over s n plus 1, and then show that the Laplace transform of t n plus 1 is factorial n plus 1 over s n plus 2, then we are done. So, we show that the Laplace of t n plus 1 is again by this recurrence relation. So, we have n plus 1 over s and the Laplace of t power n, and Laplace of t power n we assume that is factorial n over s n plus 1. So, we get this factorial n plus 1 over s n plus 2. So, we have this formula to get the Laplace transform of t n. Laplace of t n is factorial n over s n plus 1, and the real s. So, real part of the s is 0, greater than 0. In fact, we can also extend this result, because here what we have seen that this was for n positive integers. So, we can extend this result for non-integer values of n, and that is the next example we will see. So, in this case we take t power nu for non-integer values of nu. So, find this Laplace transform. We will go again by the definition. So, 0 to infinity e power minus s t and t power nu dt, and nu is greater than minus 1. This is very important, because only for these nu, when nu is greater than minus 1, this integral converges. So, we should have this nu greater than minus 1, otherwise this does not make sense. So, now we substitute this s t to a new variable u, and then we get this du is equal to s dt, and that is for simplicity we assume that s is real and positive. So, now the limits will remain 0 to infinity e power minus u, and t is u over s power nu, and dt is du over s. So, what we have s power nu and 1 s is sitting here. So, we get 1 over s power nu plus 1, 0 to infinity e power minus u and u power nu du. And now, if we recall the definition of gamma function. So, the gamma p is defined as the gamma p is equal to 0 to infinity u power p minus 1 e power minus u du. So, we have a similar integral there, e power minus u du, and u power p minus 1. Here we have u power nu, that is nothing else. We can write this nu is equal to nu plus 1 and minus 1. So, we have exactly the same form for the gamma. So, the p here is nu plus 1. So, this Laplace of t nu will be the gamma nu plus 1 and this s power nu plus 1 for nu greater than minus 1 and we have taken this as positive. So, we got a rather general result, t power nu is equal to gamma nu plus 1 s nu plus 1, and in fact one can see that if you just take these integers here nu to be 1, 2, 3 and so on, then this exactly reduces to what we got earlier. So, the Laplace of t power nu is factorial nu over s power nu plus 1. So, this is the rather general formula for getting the Laplace transform of t power nu. Okay, so now next example we have let this f t is a 0, it's a linear combination of these t's. So, we have a 0s plus a 1 t plus and so on a n t n. So, it is a polynomial of degree n in t. Now, we want to find this Laplace of this function. So, what we do, as I have mentioned already, that these transforms enjoy the linearity property. So, here we can apply this Laplace transform to each term. So, we have Laplace transform of f t is Laplace transform of this sum here a k t k k 0 to n, and this is we can also say, due to the linearity of this Laplace integral, we can write this 0 to n and a k, that is a constant term. So, 0 to infinity e power minus s t and t k dt, and this is exactly what we were talking about, the linearity of the Laplace transform. So, we can have this k to n and this a k and the Laplace transform of t k, and this we know. So, Laplace of f t is a sum k 0 to n a k factorial k over s k plus 1, because this n we have assumed to be integers. So, we apply this formula for Laplace of t power k. One remark about the series of functions. So, for an infinite series, so this was a finite series. So, this was the sum of n terms, but if we take the infinite series n 0 to infinity a n t n, then in general it is not possible to obtain Laplace transform of the series by taking the transform term by term. So, if we have finite term, then we can apply the Laplace transform term by term to this sum. But if we have infinite series, then this is not always possible to apply this Laplace transform term by term, and we need to take extra care to evaluate the Laplace transform in that case. So, let us just have a look on this example. So, we want to find the Laplace transform of e power minus t square, and we can write this in as a series. So, n 0 to infinity minus 1 n and t square power n. So, t power 2 n and factorial n. And now, let us see what will happen if we apply the Laplace transform to each of these terms. So, we have summation n minus 1 power n over factorial n and the Laplace t power 2 n. So, this sum n 0 to infinity minus 1 power n over factorial n, and the Laplace transform of t power 2 n, we know that is factorial 2 n over s power 2 n plus 1. And now, let us simplify a bit more. So, this is nothing 1 over s we have taken from here, n to infinity minus 1 power n, and then 2 n minus 1 up to n plus 1, then you have factorial n that get cancelled with this factorial n. So, we have this series. So, we just assume that this is A n, this is alternative series. And the interesting part here is now that this the A n as limit n approaches to infinity is not 0, because this here numerator grows faster than the denominator, and therefore, this transform series what we got by applying this transform term by term does not converge for any value of s. And however, the Laplace transform of e power minus t square, it is simply 0 to infinity e power minus s t minus t square, and it is very clear that this integral exists, because this e power minus t square is in fact bounded by 1. So, this integral is bounded by the Laplace of 1, that is 1 over s. So, this Laplace exists, even though if we apply to the series here the Laplace transform term by term, then the transform series does not converge. So, we have to be very careful here. So, just a note about this without going much into the detail. So, if a series is convergent before, that means the original series is convergent, the given series is convergent, and the series after taking the Laplace transform is convergent, that means both the original and the transform series both are convergent, then it is possible to obtain the Laplace transform of the series by taking the transform term by term. So, at this point we need to be careful while working with the series. We have to see whether the transform series converges or not. Okay, the next example, that is a sine square root t, the Laplace of sine square root t, and we have the sine square root t, that is a series of this sine function. So, we have t power half minus 1 over factorial 3 t power 3 by 2. So, it is basically the cube of this square root t, and plus 1 over factorial 5 t power 5 by 2, and minus 1 over factorial 7 t 7 by 2, and so on. So, obviously, this series is convergent and the value is sine square root t. So, we do not have to worry about the convergence of this series, but if we take the Laplace transform term by term, so we have Laplace of t half, and then again the linearity of the Laplace transform tells that this constant you take out 1 over square factorial 3, the Laplace of t 3 by 2 plus 1 over factorial 5, and then the Laplace of t 5 by 2 minus 1 over factorial 7, and the Laplace of t 7 by 2, and so on. So, we apply the formula to get this Laplace transform of t half, that is nothing gamma half plus 1. So, 3 by 2 and s 3 by 2 minus 1 over 3, the Laplace transform of t 3 by 2. So, the gamma 3 by 2 plus 1, so gamma 5 by 2, s power 5 by 2, and so on. Now, let us take this common. So, what exactly this is? The gamma 3 by 2 is half gamma half. So, it is half square root pi. So, half is here and the square root pi, and s 3 by 2. So, we are taking this term out of this series. So, we have this first term as 1 minus 1 by 2 and square root pi we have taken out, s power 3 by 2. So, we remain with s here, and there we get 5. So, 3 by 2, and this is factorial 3. Then here we have 1 over factorial 5. From this gamma we get 5 by 2, 3 by 2, and 1 by 2 root pi we have taken out, and this s3 by 2 we have taken out. So, it's s square minus 1 over factorial 7, and from this 9 by 2 this gamma we have 7 by 2, 5 by 2, 3 by 2, and then half gamma half. So, that we have taken, and then s cube. So, let us simplify this. So, we have this 1 over 2 s, and then we can write this square root pi over s, a better, a nicer form, and then we have 1 minus here the 3 factorial 3, we have 3 into 2. So, 3 gets cancelled, we have 2 square s. Again here the 5 will get cancelled, we get here 4, and the 3 also gets cancelled. So, we have 2 square, and then we have 2 square here. So, 2 square s and the whole square. Similarly, here we get this 1 over factorial 3 and 1 over 2 power 2 s on the cube. And if we see here, this is obviously a convergent series, and the value is the exponential minus 1 over 2 square s, that is minus 1 over 4 s. So, in this case, this is the Laplace transform of this sine square root t, because the series, the transform series is also convergent, and in this case we get this transform taking the Laplace transform term by term. Okay, so we have seen so far some basic examples of Laplace transform and the definition of this Laplace transform. Now, we will be talking about the existence of the Laplace transform. So, the first question is whether the Laplace transform exists for any function, and obviously the answer is no, because of the convergence of that integral. That integral will not converge for any function. So, there is a class of function, for that class only that integral will converge and the Laplace transform will exist. So, we will see just a function here f t is equal to t square, for example, and then we try to get the Laplace transform by this limit r to infinity 0 to r e power t square minus s t dt, and as you see this integrand grows without bound. So, this integral is, the value is infinity. For any choice of s, whatever s we take here, this integral will be infinity. So, this integral is not convergent. So, the Laplace transform of e t square does not exist. Then the question is that for which class of functions the Laplace integral converges. And to answer this question, we have to give some definition, and the one is piecewise continuity. So, what is piecewise continuity? As by the name, it is a piecewise continuity. The functions are not continuous, but they are continuous in pieces. So, a function f is said or is called piecewise continuous on a closed interval a b if there are finite number of points t 1, t 2, t n such that the function is continuous on each open subinterval. So, a to t 1 function is continuous, t 1 to t 2 it is continuous, t n to t b it is continuous. So, the function is basically continuous everywhere other than these points t 1, t 2, t n. And so, in addition to that, the following limits should exist. What are these limits? These are basically the left limit of the function as t approaches to a. So, to this end a, and the right limit here as t approaches to a, and the left limit as this t approaches to b of the function f t, they should exist. And at all these points t 1, t 2, t n where the function is not continuous, both the limits, the left and right limits, both should exist for all j's. So, j 1, 2, 3 n. So this is a piecewise continuous function. So the function is basically continuous other than these points t1, t2, tn, and if the following limits exist, then the function is said to be piecewise continuous. Just to add here, a function is said to be piecewise continuous on 0 to infinity if it is piecewise continuous on every finite interval 0 to b, and b you can we can take any positive number. So in this case we call that this function is piecewise continuous on 0 to open infinity here if it is piecewise continuous on every finite interval we take from 0 to b. Okay. So let's look for some examples of this piecewise continuous functions before we go to the next definition. And this is a typical example of a piecewise continuous function. So here the t, as t approaches to a, then this right limit exists and the function is not continuous at these points t1, t2, tn, but the limits as t approaches to this t1 from this left side or t approaches to t1 from this right side, the both should exist at all these points of discontinuity, and here the right limit as t approaches to b should also exist. So this is a typical graph of a piecewise continuous function. So we take one more example of this piecewise continuous for this piecewise continuity. So let's discuss the piecewise continuity of the function f t is equal to 1 over t minus 1. So what will happen here? So the problem is at t is equal to 1. Other than that, the function is continuous and we do not have any problems. We do not have to check anything else other than the limit as t tending to 1 from the right side as well as from the left side. So if we take a look on the plot here, so as t approaches to 1 from the left side or from the right side, the limit does not exist. So then the function this 1 over t minus 1 is not piecewise continuous in any interval which contains this 1. So this function is not piecewise continuous. The another example, if we have this function f t 1 minus e minus t over t as t not equal to 0, and we have 0 when t is equal to 0. So we have to check whether this function is continuous or not. So again we have problem at t is equal to 0. So just to note that I'll go back again to this example 2. The function in fact written in this form is not defined as t is equal to 0. So we need to define this at t is equal to 0. So we can set this function at t is equal to 0 again 0 like here, and then discuss this piecewise continuity. So let's now come back to this example. So this where t is not equal to 0, it's 1 minus e minus t over t, and when t is equal to 0 it's 0. So we have the problem at t is equal to 0 only, otherwise this function is as a nice function, it's continuous, so there is no problem. So at t is equal to 0, if we take the limit, the left limit or the right limit, so if we take this right limit 1 minus e minus t over t, so it's getting 0 by 0 form, so we can apply this L'Hopital rule. So the differentiation of the numerator will give us e power minus t, and then this will be positive, so e power minus t over 1, and then t approaches to 0, we will get 1, and also when t approaches to 0 from the left side, the both limits are 1. So the function is piecewise continuous in this case. So, a very important consequence of this piecewise continuity is that the function is bounded basically, because at all these points when we have problem, the limits exist, and then we have actually the boundedness of the function. Okay. So, we go to the next definition, and that is function of exponential order. So, what are these functions? So, a function is said to be of exponential order alpha if there exist constants m and alpha such that for some t naught greater than 0, this inequality holds that the absolute value of this function f t is bounded by this exponential function for all t greater than or equal to t naught. So, basically the growth of the function is bounded by the exponential function with this exponent alpha, and then we call that the function is of exponential order. In practice, this is difficult to check this inequality for checking whether the function is of exponential order or not. So, for that we have an alternative definition. So, a function is said to be of exponential order alpha if this limit t tending to infinity, and we take this f t with the absolute value and this e power minus alpha t. So, if this limit exists, of course, as a finite quantity, then we say that the function is of exponential order. Geometrically, if we see, this is basically the graph of a function f t, and this is our exponential function with exponent alpha. So, the graph of f on the interval t naught to to infinity here does not grow faster than the graph of exponential function m e alpha t. So, that is the meaning of this functions of exponential order. So, let us take some example of these functions. The first example show that the function f t t power n has exponential order alpha for any alpha and for any n, the set of this natural number. So, whatever n we take here, this is always the growth of this function is bounded by the exponential function of order alpha for any alpha positive. So, it is very interesting to see. So, now we see the limit t tending to infinity e power minus alpha t and t power n. And so, if we let this t tending to infinity, it is basically infinity, and over if we write this t power n over e power alpha t. So, it is infinity by infinity form. So, we can apply the L'Hopital rule n times to get this factorial n out of this t power n when we differentiate this n times, and then e power alpha t, here we will get alpha n e power alpha t, and if now we let t tending to infinity, we see that this is 0. So, this function t power n is of exponential order for any n and for any alpha. So, example 2. So, if we have function f t power t square, and we will see that this is not of exponential order, and the reason is clear, because if we take this limit t tending to infinity and e power minus alpha t e t square, that is the limit t tending to infinity e power t and t minus alpha, and whatever alpha we have as t tending to infinity, this is going to be infinity. So, for all values of alpha, this limit does not exist. So, this function e t square is not of exponential order. Now, we come to the sufficient condition for existence. So, if f is piecewise continuous on 0 infinity and of exponential order alpha, So, the function is piecewise continuous and it is of exponential order alpha, then the Laplace transform exists for real s greater than alpha. And in fact, we have more stronger result. That means that under these conditions, that the function is piecewise continuous and of exponential order, the Laplace integral, the 0 to infinity e power minus st f t dt converges absolutely. So, we have a rather general results under these two conditions, that the function is piecewise continuous and of exponential order, then this converges absolutely. And we can quickly take a look at the proof. So, we have that the function is of exponential order, that means the f t is bounded by m 1 e power alpha t for certain t naught, t greater than t naught, and also the function is piecewise continuous, then this is bounded from 0 to t naught. We can combine these two conditions to have one bound on the f t for the whole t. So, this f t we can find a m easily, such that we have the absolute value of f t bounded by m e alpha t for t positive. And in this case, for example, alpha is positive, you can simply take the maximum of m 1 and m 2 to get this m. So, now let us take a look 0 to r and the e power minus s t f t with the absolute value d t, and this is bounded by 0 to r, and e power s we take x plus I y and then t and then m e power alpha t dt for this f t, and that is bounded by this m, and e power minus x and this alpha we combine, and this I y t absolute or e power minus I y t with the absolute value, that is 1, and then this integral we have m over x minus alpha minus m over x minus alpha e power minus x minus alpha r. And now we let r to infinity, and note that the real part of this s, that is x, is greater than alpha, then we get basically this will be 0 and this value is bounded by this. So, we have seen that this integral, in fact, with the absolute value of this integrand, this is bounded by m over x minus alpha. So, the Laplace integral converges absolutely for real s greater than alpha, and of course, this converges for real s greater than alpha. So, that was the sufficient condition for the existence. So, now the quickly two remarks I am going to put. The first remark is that we observed that the 0 to infinity e power minus s t f t dt, the absolute value of this is bounded by 0 to infinity, and we can take this absolute value inside. So, e power minus s t f t dt, and this we have seen that this is bounded by m over real s minus alpha for real s greater than alpha. So, what is interesting to see here, that if we let this real s to infinity, then what will happen? This will go to 0, and we have the Laplace transform of any function, which is of course piecewise continuous and of exponential order. So, e power minus s t f t dt, or we denote this by f s, will go to 0 as this real s go to infinity, because this term will go to 0. So, what we can conclude from here, that if Laplace of f t does not go to 0 as s tending to infinity or real s tends to infinity, then f t cannot be piecewise continuous function of exponential order. For example, if we take or if we consider these functions f 1 s is equal to 1 and f 2 s is equal to s over s plus 1. So, they are not Laplace transform of piecewise continuous functions of exponential order, because this f 1 s does not go to 0 and f 2 s does not go to 0 as s approaches to infinity. But this does not mean that they are not the Laplace transform of any function, but at least they are not Laplace transform of piecewise continuous function of exponential order, that we can conclude from here. The remark 2, it should be noted that the conditions stated here in this existence theorem are sufficient rather than necessary conditions. That means, if these conditions are satisfied, then the Laplace transform must exist. If these conditions are not satisfied, then the Laplace transform may or may not exist. So, these are the sufficient conditions. What are the sufficient conditions? That function should be piecewise continuous and it should be of exponential order. In that case, we are sure that the Laplace transform will exist, but if these conditions are not satisfied, the Laplace transform may or may not exist. So, to support this remark, we have two examples. So, the first one is this function t is 2t e t square cos e t square. So, let us consider this function and note that this function is continuous on 0 to infinity, but not of exponential order, because e t square is sitting there. However, the Laplace transform of this function exists, because the Laplace transform as per the definition we have 0 to infinity e power minus s t 2 t e power t square cos e t square dt, and then integrate by parts. So, we have e power minus s t and the integral of this e sin e t square, and then again here this differentiation of this will give us minus s. So, we will get here plus s, and then this term will go to 0 as t tending to infinity, and as t approaches to 0 this will be sin 1. So, with minus sin 1, and here we have the s, and this is nothing a Laplace transform of sin e t square, and the sin e t square, this is of course a continuous function, and this is a bounded function. So, it's of course of exponential order. So, the Laplace transform of sin e t square must exist. So, this Laplace transform of f t exists because this is minus sin 1 plus s, and the Laplace transform of sin e t square. Let us take the another example, that is f t is 1 over square root t, and this function is not piecewise continuous function, because as f t approaches to infinity, as t approaches to 0. Sorry, it's 0. So, the function is not piecewise continuous, because f t approaches to infinity as t approaches to 0, but the Laplace transform of this f t is minus half plus 1 and s minus half plus 1. So, that is square root pi over s for s positive. So, we have these two functions, one of them is not of exponential order, the other one is not piecewise continuous, but the Laplace transform exists in both the cases. So, this supports the point that those conditions are sufficient conditions, not the necessary conditions. So, we have now the sufficient condition for the Laplace transform, that the function should be piecewise continuous and it should be of exponential order. So, that is all for this lecture. Thank you.